Okay, let us now discuss the same problem of large deviation, but in the case where the random variable x are continuous, and so they have PDF, let's say, so we have random variables, sequence of n random variables, n, the xi are real random variables, and they are drawn from a PDF which is Q of x. Okay, and now we assume that Q of x has thin tails, so which means that it decays faster, so at least as fast as an exponential, okay, as x goes to plus minus infinity. As e to the minus lambda x. So for some positive lambda, okay? So the case where the PDF decreases slower than exponential will be discussed later, okay? Okay, so then again we are interested in this large deviation event. Now, however, I have to define this large deviation event as the event that for my sample, the mean of the xi is in an interval x bar plus dx bar, because the random variables are finite. So the probability of this event an of x will be proportional to, I can write it as Pn of x times dx, because it will be proportional to dx. And if you want, this Pn of x is the PDF of the random variable x bar, which is 1 over n somewhere I of the xi. I want to compute how is this, what is the form of this PDF, okay? So the way to do this calculation is rather straightforward. So if we want to compute the PDF of the average, then what we do is take an integral from minus infinity to infinity dx1 q of x1 infinity dxn q of xn, and then we impose a delta function. We impose that x bar should be exactly equal to the mean. Okay, so well, you know the delta function, the property of the delta function, I assume. So what we are going to do is to use the representation of the delta function, the integral representation of the delta function, which is this one, with minus with ik x bar. And we are also going to use the property that delta of ax is equal to 1 over a times delta of x. So delta behaves as 1 over x essentially. as the dimension of 1 over a, like any probability distribution or any PDF. Okay. So if we use these two properties, then first of all we are going to change these into n times delta of n times x bar minus the sum over I of the xi. And then using this, we can rewrite this as n times the integral in dk over 2 pi minus infinity to infinity. Then we have the integral dx1 of q of x1, integral dxn q of xn of e to the I k times n x bar minus I k sum over I of the xi up to n. Okay. Now you see that this integral can be factorized. So there is this part that does not depend on the xi that can be put at the beginning. So this is n times integral minus infinity to infinity dk over 2 pi e to the I k n x bar. And then what you have here is n integrals. I mean this term, which is a sum over I of the xi, and the exponent can be written as the product of ikxi minus ikxi e to the minus ikxi, and this can be distributed in each of these integrals that can be factorized. So at the end of the day, what you're going to have is just an integral from minus infinity to infinity in dx of q of x e to the minus iq x raised to the power n. Okay, so what you recognize here is again this is the expected value over the distribution q of e to the minus iq times the random variable x. Okay, which is the characteristic function. Okay, so very good. So however, now contrary to what we did in limit theorems, we are going to study large deviations. Okay, so then you see that you can rewrite this integral as n times an integral from minus infinity infinity in dk over 2 pi of e to the n times a function computed in ik. So and this function g of let's call it beta is beta times x bar plus the log of the expected value over q of e to the minus beta times x. Okay, so this is the result. So what should we do? What we can compute this integral by the saddle point method. Okay, saddle point method means that we have to find say the beta that for which the first derivative of g of beta is equal to 0. So the first derivative of g is equal to x bar minus the expected value over q of e to the minus beta x times, well, when I take the derivative of the expected value of q of e to the minus beta x, I get a minus times the expected value over q of x times e to the minus beta x. Okay, now, well, first of all, you can recognize that this object here is exactly equivalent to the z of beta that we defined before. Okay, and in addition, this object here is exactly equal to the expected value of x over a modified distribution, which is p beta of x, which is q of x e to the minus beta x divided by z of beta. Okay, so when you solve this equation, that the first derivative of g has to be equal to 0. So this equation is very similar to the equation that we had before, because it tells you that x bar must be equal to the expected value over this modified distribution of x. Okay, so let's say that this identify my beta star. And then what I need to do is to expand g of ik around beta star. So this will be equal to g of beta star plus ik minus beta star times g prime of beta star plus 1/2 ik minus beta star squared g double prime of beta star plus higher order terms. Now again, you realize that when I've chosen beta star so that this is equal to 0, so the first term does not exist. And then what I can do is to substitute this expression here, and then as a result of this, this integral becomes approximately asymptotically equal to n times e to the n times g of beta star, which is the first term, and then I have an integral from minus infinity to infinity in dk over 2 pi of e to the so this term here I can take the I outside, and this will be n minus n divided by 2 g double prime of beta star times k plus I beta star squared plus higher order terms. So again, like in the law of large numbers for some, now if I make a change of variable in this integral where say I write z, I use the new variable z, which is the square root n g double prime of beta star times k plus I beta star, then this integral becomes a Gaussian integral, and what you can see is that all these higher order terms contribute to corrections that vanish as n goes to infinity. So asymptotically I can estimate this integral as just square root of n divided by 2 pi times the second derivative of at beta star times e to the g of beta star. Okay, so this is essentially the result. What is the probability of the large deviation? Okay, and again, beta star is a function of x bar because of this equation here. Okay, very good. So now, in order for all of this to make sense, one condition that has to be satisfied is that the second derivative computed in beta star should be positive. Okay, so what is the second derivative of g? Well, the first derivative is given by this formula here, and as we said, it is equal to x bar minus an expected value over beta of x. So the second derivative of g is minus the derivative with respect to beta of the expected value over beta of x. And this is a calculation that we have already done, and you can check that this gives you the variance under the distribution p beta of x. Okay, so this is the variance under this distribution p beta of x. Okay, so this tells you that this is positive, because variance is, well, actually strictly positive, so that this calculation makes sense. Okay, then the next thing that you can check is that if we ask what is the form of this g of beta star, then so g of beta star is equal to, well, we can take this equation here, and so the equation is equal to beta star times x bar minus plus the log of this the log of z of beta. Okay, but beta star is such that you can also write this as beta star times the expected value over beta over this distribution p beta of x, when beta is equal to beta star, plus the log of z of beta. Okay, and and you can check easily that this is exactly equal to minus the Kullback-Leibler divergence between the PDF P of beta star and the original PDF Q. Okay, because if you substitute the expression for P beta star, this is exactly what you get. So we recover exactly the same result as before, that the probability of the large deviation is exponentially small with a coefficient which is equal to the Kullback-Leibler divergence between the closest distribution to Q in terms of the Kullback-Leibler divergence. Again, you can also check that the marginal distribution of a finite number of variables conditional on the large deviation is given by, so if you compute the marginal distribution of m of these random variables conditional on the large deviation, then you can check that in the limit when n goes to infinity, this is exactly the product of the random of the PDF p beta star computed in the variables x1, xm. So this tells you that the large deviation is realized as a draw from independent and identically distributed random variables which take value x1, xm. Okay, so very good. So let me summarize this. Let me summarize what we have said so far, and in a specific recipe. So if you have this sample and you want to study the probability of this large deviation or observing a large deviation of x bar, then generally what we have seen is that this probability is exponentially small in n, and we are going to call this function I of x the large deviation function, and is also called the Kramer function. Okay. Okay, so the problem in large deviation is how to compute this large deviation function as a function of x bar. And here is the recipe. So first you compute the cumulant generating function. So compute the Q1 generating function, which is the log of the expected value over the original distribution, so which is the distribution from which these random variables are drawn, of sorry, let me take different convention of signs, h times x, where my h here is what I called minus beta before. Okay, so the second step is that you should compute the first derivative of this function, and this defines what we have called before the expected value on this modified distribution of x. So let's call it x bar of h. Okay. So then the third step is that you should invert this function here, so the first derivative of phi, and get a function h as a function of h bar. Okay. And then the fourth step is that you can compute the large deviation function as x bar times h of x bar minus function phi computed in h of x bar. Okay, so if you look at the steps that we have been doing before, they essentially can be summarized in these 4 steps, and these 4 steps are essentially what one calls a Legendre transform. Okay, so the reason why you get the Legendre transform is not at all a coincidence, as we will see. And so let me remind you a few facts of the Legendre transform. So in the Legendre transform, these two variables here are called conjugate variables. And the Legendre transform transforms a convex function phi into a convex function I. Okay, and phi is also the Legendre transform of I. So this is a reversible transformation. So let's make a simple example of this. And so let's apply this recipe to a simple distribution where q of x is just an exponential, e to the minus x for positive x. Okay. Then, okay, so the first thing that we should do is to compute phi of h. This is the log of the integral from 0 to infinity dx e to the minus x plus h times x. So this is the log of 1 divided by 1 minus h, okay, or minus the log of 1 minus h. So the derivative, the second step, we take a derivative, and the phi dh is equal to 1 over 1 minus h. So this, we call it h bar, x bar of h. And so the third step is to invert this relation. And so you take 1 over x bar, so you get that h of x bar, if I'm not mistaken, should be 1 minus 1 over x bar. Okay? Very good. So now okay, so now the final step is to compute I of x bar as x bar as using this equation here. So it's x bar times 1 minus 1 over x bar minus phi of x, which is plus log of 1 over h, which is log of x bar. So this is x bar minus 1 plus the log of x bar. Okay, so let's see how this function behaves. So you see this function, if I compute this function I of x bar as a function of x bar, then first of all you can find that I, when x bar is equal to 1, is equal to 0. So in 1 this function must be equal to 0. And then you find that this diverges logarithmically when x, sorry, let me write it a little bit better. So this diverges logarithmically when x goes to 0, and it also diverges linearly when x goes to plus infinity. Okay? So, so this fact here, the fact that this Kramer function vanishes at x equal to 1 is essentially consistent with the law of large numbers, because the expected value over q of x in this case is equal to 1. So we expect that when x bar is equal to 1, so the mean takes the typical value, and so the probability should not be exponentially small. The second thing, you can check that if you look at an expansion close to x equal to 1, then what you observe here is that if you take a second derivative of I of x, then this is equal to minus 1. So the second derivative of x bar is equal to minus 1 over x bar. If I compute it in x equal to 1, then this should be negative, right? So I think here there is a sign problem, so this should be a minus sign here. This goes as minus log of x bar goes to infinity when x bar goes to infinity. So the second derivative is 1 over x bar. So in 1, this is just 1/2 x bar minus 1 squared plus higher order terms. And you can check that this behavior, this parabolic behavior of the Kramer function is consistent with the central limit theorem. Indeed, the coefficient that you have here should be 1 over 2 times the variance of x. Okay, so this to summarize, so this function, this Kramer function here, contains in itself the law of large numbers, the central limit theorem, but it gives a lot more information on what is the probability of large deviations of the sample mean from its expected value.